Alright, so this is part 2 or a continuation of my previous video that was titled Particle in an Infinite Potential Well, and then the energy was in parentheses. So in that problem I was solving for a particle sort of bounded in a region of infinite potential on either side of it between 0 and A. So that was the potential well, or infinite potential well rather. So this is a continuation of that. So recall that I found the wave function to be psi equals d sine square root cx. Alright, so the energy that was found in that video was E equals n squared pi squared h bar squared over 2ma squared. So this is the energy of a particle in an infinite potential well. And here you have n can be 1, 2, 3, dot, dot, dot. So it could take on any integer value from 1 to essentially infinity. And this produces the corresponding energy for the particle in this system. So we had C in the previous video. This is just a constant that was set to 2me over h bar squared. Alright, so that means square root C is equal to 2m over h bar squared times energy, which we found to be n squared pi squared h bar squared over 2ma squared. So the h bar squared cancels with this h bar squared, 2m cancels with this 2m, and then all you're left with is n squared pi squared over a squared. This is all being square rooted, so everything here essentially reduces to n pi over a. Now, this is what square root c is, so we basically plug that in. So we get our solution that psi has to equal d sine of n pi x over a, essentially. Now also recall that perhaps I didn't explicitly show, but the Schrodinger solution, or the wave equation itself, is actually a form of psi of x of t. So it's position as well as time dependent. Normally, in this situation we argue time independence, so we're only focused on the psi of x portion. Really, this wave function, for time independence, we would argue that it takes on the form something like that. I don't know if it gets. I try to squish that in there. That's a chi, sort of like a x with a curvy sort of thing at the end. So this is a separation of variables method that you would normally enforce in this case. So what I was doing was only looking at the psi of x components. So the wave function respective position, rather. And this is what this is. There's no t component here. We could also solve for that, but that wasn't what I was fully looking for in this case. So then we have, so now this is our wave equation. Psi of x equals d sine n pi x over a. Okay, so what do we do now? Well, there's one more thing we could do to sort of finalize this result and find out what d is we argue that, or recall that, the probability is essentially equal to, which is this is direct notation on essentially for an inner product. So in this instance, it would be the psi complex conjugate of our wave function psi times itself dx. So the probability to find it essentially in all space from negative infinity to positive infinity should be equal to 1. Does that make sense? There's should be 100% probability to find this particle in all space. Now, our wave function only exists essentially from 0 to a. It's zero everywhere else. So the limits of integration can actually be changed to be from 0 to a, because I'll sort of draw here. So we have psi So it is n pi over x. So it's sort of like 0, 0, 0, 0, and then it could, let's say, take on this form and keep going to 0. So I guess this would be for the n equals 1 case. This sort of waveform changes depending on the n value. So essentially that's how it only exists in that area, and essentially as this is an integral, we're essentially finding the area under this graph, and since it's 0 everywhere else, the area under there is 0, so it's meaningless to take limits integration from there. We only take it where it exists, essentially. Alright, so plugging that in, psi star x, as I said before, is the complex conjugate. So in this case, we don't have an I value, imaginary unit, in our wave function, so we don't need to worry about it. Essentially, psi star x equals psi of x, so they're equivalent. So you essentially have psi squared. So squaring that would be squaring the constant and then squaring the sign. Alright, so now we could bring this out. This is also equal to 1. So we have now the d squared coming out on the outside. So then it's the integral 0 to a sine squared n pi x over a dx. Now here we have to use a trig identity to substitute in. So I use taking sine squared of, let's say, some arbitrary value b. So the identity for this is half times 1 minus cos 2b. So in this instance, our b is n pi x over a. Hence, we can substitute this in. And then expanding the half onto both of these terms, we get half minus half cos 2b, which is 2n pi x over a dx. Alright, so now we just take the integral of this. So the integral of half is just half x. The integral of half cos 2n pi x over a is half, or it'll be half. Then this inside essentially has to come out but flipped. So we have a over 2n pi a, sorry, a over 2n pi, and then it's also sine 2n pi x over a. And this is being enforced through the limits 0 to a. Alright. So this gives us d squared there. We plug in the first upper limit is half a minus a over 4n pi sine of 2n pi. Okay, so okay, I'll write out the full thing actually. So then we have enforcing the lower limit, we subtract it, so it's half 0 minus a over 4n pi sine of 0. Okay, so recall sine, let's say it was sine of x. So arbitrary. Essentially it takes on this sort of form. If it looks like it's damping, it's not. It's only a mistake of the artist. It's 2 pi, 4 pi here, 6 pi, 8 pi. So you can see a pattern. So plugging in any value for n here, being n being an integer, from essentially 1 to infinity, we always get 0. So no matter what n is, 0 here. So this equals 0. Half times 0 equals 0. Sine of 0 equals 0. So essentially this whole integral just reduces to half a. So the whole area underneath the curve is equal to half a. And notice that this is for any n. So an entire area, no matter the end value for the wave function is always going to be half a for this problem. So now we have 1 equals d squared times half a. Hence now we could isolate for d simply by algebra. So bringing half a over to the other side gives us d squared equals 2 over a. Taking the square root of both sides then gives us d equals square root of 2 over a. Hence we now found what our constant should be equal to. So now we recall the wave function is equal to psi of x equals d, which we just found. So that's square root 2 over a. And then the rest of it is sine n pi x over a. So this is our wave function for this particle in an infinite potential well between the regions 0 to a where it exists. So in a way, I suppose the quantum mechanical analog of the classical equation of motion is essentially this wave function. However, you don't necessarily have a trajectory or a trajectory model anymore. It's sort of like this wave equation is itself this sort of equation of motion, but instead rather describes the probability, sort of like a probabilistic framework. So it describes the probability of the probability of finding a particle in a certain region. So you would take the limits of integration rather than through all space. You could take it from, let's say, 0 to half a. So what's the probability of finding it there? We could actually you could actually do that problem, which I'll probably explore in another video. For in this case, we're just setting it to all space because that's so we could get our d value, because we knew that it was supposed to be equal to 1. So it gives us the probability. Alright, I'll see you guys later.